this. All right. So, oh, too soon. Starting a new section, section 7.2, which is going to look a lot like 7.1, where we introduced numerical data last day, and we talked about one sample mean questions. Oh, but before I forget, nice try, Emily. Nice try. Hey, this isn't refreshed. I posted a practice 4 test 2. You'll see why I emphasize the 4 if you haven't opened it yet. Because let's see here, where is it? Practice 4 test 2. So we're going to cover the topics, possible topics that could be on test 2. One sample proportion, hypothesis testing, confidence intervals, sample size calculations. 2 sample proportions, we did hypothesis testing, confidence intervals. Chi-squared goodness of fit test is just a hypothesis test for more than 2 groups, right? One sample mean, hypothesis testing, and confidence intervals, that's just from Monday. And then paired numerical data, which is what we're going to talk about today. Hypothesis testing or confidence intervals. Obviously, I'm not going to go hard on the paired data, but as you'll see, it's basically one sample mean all over again. Okay, and I've got all these practice problems with solutions. Feeling like a champ. I think the solutions end up being quite long, 23 pages. So I did not check them. So if you're working through them and there's something that looks weird, then just message me and I'll let you know if it is actually on the right track or what. So you have those, and then our test is on Monday. Okay. In terms of review, we did one sample mean. And what I'm going to do is just grab it from your formula sheet, right? We had one sample mean, because I want to do comparison. One sample mean question. So you're given a sample, you're told the sample mean and the sample standard deviation is how those questions are going to start. And then from there, you can build a confidence interval. The new thing that we talked about mostly last day was the t distribution, right? T has n-1 degrees of freedom if you have a sample of size n and you only have one sample. Then you take your sample size, subtract 1, and that's your degrees of freedom. And we were looking at the t table here. And we said, okay, all these degrees of freedom are on the left-hand side. And down at the bottom, it gives us the one-sided p-value or the two-sided p-value. But notice you don't really need that last line because it's just the one-sided p times 2, right? Just like we were doing for z's. And so the method that we use is just slightly different. The idea stays the same, but how we get the p-value changed a little bit, right? We first find, let's say we have a sample of size 21, which means I have 20 degrees of freedom. And then if I calculated my t is 2 even, what would I do? I would take my 2 and try to place it between these two values. So it would fall somewhere between these two values, 1.725 and 2.086, which means that my, let's say, two-sided p-value is somewhere between. You have to read these from right to left because they're decreasing as you move out further into the tail, right? The area in the tail gets smaller. So then you want to list them from smaller to larger, 0.05 and 0.1. Yeah. I am going fast, but we're about to do it all over again. Was that the door? So today, we're going to talk about paired data. So if I copy and paste these next to each other, what I want us to notice is that, okay, if I'm looking at the confidence interval for X bar, which is the one sample mean, I've got some T star and then S over root N is my standard error. Without knowing anything, I recognize that this looks the same, right? I've just got little subscript diffs everywhere. Okay. And the reason for that is because paired data is exactly as it sounds. So now all of a sudden you have 2 samples of numerical data. Okay. So we're going to look at and compare these, but as you can tell, we just do the same thing after we pull a fast one. So here, that's not really the review. That wasn't a review at all, but it's an intro. So paired data is when we have 2 samples of numerical data. 2 samples of numerical data. But both those samples are measurements from the same subject, usually. But both samples are measurements on the same subject. So some common examples are things like pre and post scores, right? You enroll in some sort of tutoring program and you do some sort of beginning test and you get a score, and then you go through the program and they teach you some stuff, and then you have your final score, and now you wrote that test, you wrote both of those tests, right? You've got a pre column. So in terms of your data set, right, whoops. Your data set is going to look something like this. So Emily wrote the test and my pre-score was 60% and my post score was, hopefully I improved, 80%. Whee! All right. And then I'll do Steve, he won't mind. Steve's pre-test was, oh, he was kicking butt, 80. But his post score, 95, wow. So here, notice that we have 2 samples, right? The pre and the post. But if I want to capture my improvement, I don't want to take an average, which is the next section where we treat these as 2 independent groups, where we would lump all the pre-scores together and talk about that average compared to the post-score average. Okay, and so that's the difference between these two sections. And so now these data are paired on who wrote the test, right? I started at a lower level, but I improved, right? It's still lower than, well, it's the same as Steve's when he started, right? And so to capture that improvement in each individual, what we do is we calculate the difference. And as long as you calculate the difference in consistently, right? I usually like to take the first column minus the second column and then deal with it. Or if you can tell, or if you can kind of glance and look at, oh, okay, I want to have positive values, then you would do post minus pre in this case. So as long as you're consistent, let me bump this up. The difference, let's say pre minus post. Pre minus post puts me at -20 here. 80 minus 95. That tells me I improved more than Steve. I'm still not doing as well as he was even in the beginning, right? But we've captured my improvement of 20, right? Versus his improvement of 15. Okay. So this is the trick that we're going to use. So we start with two samples, but if they're paired, right? So I've got two observations on one subject, then we calculate the differences and we analyze the differences. So now what happens is, and I'm going to erase these lines because they won't make sense later, but what we do is we ignore this, and now I just have one sample of differences. Maybe I'll have to keep those lines. Kind of looks weird, but right. Which means that now you're back to a one sample means question, right? And so this brings us back. So now this is a one sample means question, or mean, I guess. It's only one. One sample mean type of question about the differences. You'll be able to calculate the sample mean of the differences. So we can find, are you kidding me? This happened this morning in my other class too, but it was in the B building. So there's no, I don't understand. Today is a bad day. It's just a bad day. I was going to keep writing, but you can't see it. Okay. All right. What was I saying? We can calculate X bar, and then that's the sample mean, right? To indicate that I know that this is the mean of the differences, and to remind myself, I'm going to say a little subscript diff there. Right? Just to remind myself, especially in terms of interpretation, right? Then I want to be talking about the mean of the differences, right? And so the mean difference in scores is this, right? And so X bar diff, or sometimes if we're lazy, we just use a little d. Okay. We can calculate the standard deviation of the differences, or SD. Right, now I've got a column of differences, that's numerical data. I'll be able to calculate the mean, the standard deviation. We don't have to do it by hand, right? I'll give it to you, but just being able to pick up on a sentence structure where you're analyzing the mean difference. Okay? That's the key part. So now, if I go and it's worth adding a page here. Maybe. Let's blow this up. So paired data, or I like to call it matched pairs, just to emphasize that observations are matched, right, in pairs. So whatever you want to call it is fine. And then I've got a little reminder that we're analyzing the mean difference. Sorry. That's okay. I need one of those like buzzers or something. Buzz people in. Swings the door open. So if you ignore all the diffs, right, this is the exact same formula that we had for one sample means, which makes sense because we reduced it to one sample, right? And so these little diffs, right, they're just meant to kind of nudge you along and say, hey, do you have the differences? In terms of a hypothesis test, right, we have to assume that the pre and the post scores are the same until we have proof otherwise, right? And so for our hypothesis test, we have to assume the pre and post scores are the same until we have proof otherwise. We're analyzing the differences. So we said the difference is going to be, in our case, pre minus post. If they're the same, okay, so if pre equals post, then the difference is 0, right? And that's where we get our null hypothesis that, okay, fine. The null hypothesis for a paired data question is going to be that the mean, so the population mean of the differences, and I do want to see that diff on there. You can use a D if you want, but just to indicate that it is for the differences, is 0. We're used to having to find values and put them into our null hypothesis. But what's really nice is once you've identified a question as a paired data question, this is your null hypothesis. You're stuck, right? I'd say deciding what your null and alternative hypotheses are is often the hardest part, right? Then you're kind of on rails. And so now you just write whatever you have on your formula sheet in this case, right? We're always going to compare the difference to 0. We can get fancy and do something other than 0, but we are not going to. Hey, it looks like I forgot to delete the alternative on there. I was deleting them because I have the default, which is a 2-sided test, but then I found that that was kind of confusing for people. So this can be less than, can be greater than. The tricky part about a 1-sided test is that you want to think about what the difference would be if it's negative or positive, depending on what you want to show, right? If you want to show that the post scores are higher than the pre scores, consistently higher, so an improvement, then the difference overall would be less than 0, right? Because you're subtracting a larger number from a smaller number. So that's the tricky part. Yeah. So if we want to show, that pre is less than post, right? The difference would be pre minus post would be less than 0, right? So then in that case, your alternative hypothesis would be that mu diff is less than 0. Oops. If you don't like this, that thought process can be a little bit tedious sometimes. What could you do? You could just pick some test values that reflect the scenario that you want, right? So here, well, 80 is a higher score than 60, right? I get a negative number, so it must be less than 0, right? So you can kind of guide yourself there. Okay. Then, once you have your null and alternative hypotheses, then do the test, right? The test is the same as for one sample means. You've got your X bar, but your mu naught is forced to be 0, right? We're always comparing it to 0. How far is the mean of the differences from our sample from 0, right? If it's far, we reject H naught. If it's not far, then we don't reject H naught, taking into account the standard deviation of the differences and the square root of the sample size of the differences, okay? And so that can be confusing sometimes, right? Remembering that even though I give you all this information, what we're analyzing is this group, right? So in terms of your sample sizes, it's however many subjects you have, right? That can be confusing, I know that. Degrees of freedom, we calculate a t, so we need the degrees of freedom is the number of the differences minus 1. Ta-da! There, on to the next topic. No, let's do an example. Okay. 200 observations were randomly sampled from the high school and beyond survey. The same students, took a reading and writing test, and their scores are shown below. At first glance, there's a lot of typos in these ones, sorry. At first glance, does there appear to be a difference between the average reading and writing scores? I don't think so necessarily, right? We've got more spread in the reading scores, and the writing scores are kind of more similar, but they're all hovering, right? This is the median, this is the median. They're all hovering around the same areas. And so I wouldn't say that there's a huge difference here. When would we say there's a difference? Well, if we had, can you see? Yeah. If this was just shifted up, right, or down, or if there was very little overlap, then we would say that there was a difference, or we suspect there's a difference. So our data set might look something like this. So I've got a decoy ID number. It's a decoy because it looks numerical and you might want to analyze it, but don't, right? Because there's nothing to know about the ID number. We've got the observation number, which I probably would have just used instead of the ID number. But then we've got their reading scores and their writing scores. So notice that student 1, let's call it, had a reading score of 57 and a writing score of 52. And so are the reading and writing scores independent of each other? No, because they're measurements from the same student, right? It's not unreasonable to think that if your reading skills are high, then your writing skills are probably also kind of following, right? If your reading skills are low, then your writing skills are probably also low, right? They go hand in hand. And so that's just the answer. So what can we do? We could calculate the differences in the scores, which is what we do. So we've got the reading and the writing score, and then we calculate a new sample of the differences. And what we can do is we can look at the distribution of the differences if we want to, because that's now our sample. And in terms of our assumptions, right, we have a sample of size 200 students. And so our sample size is large enough so we can go ahead and do this, this test. Okay. But also it looks approximately normal. And so that's definitely a reason to do it. I'm not going to write that down because I am pretty sure there's a slide on it in a bit. So we're interested in the population mean of the differences, right? Overall, all these high school students, what's the difference or what's the mean difference in the scores? Our best guess, our point estimate is going to be that sample mean of the differences. Hey, I didn't read this. This is wrong. I just skimmed it. What are the hypotheses for testing if there's a difference between the average reading and writing scores? Well, this is all I want to see, so let's just stop there. If I want to know if there's a difference, right, then my alternative is going to be mu diff is not equal to 0, right? That difference, I don't want to know if it's less than or greater than. And in general, I try to be nice for paired data because it involves all that thought, figuring out if it's positive or negative, right? And so usually I want to test if there's a difference in the mean differences. So you can see how that gets boggy, right? Is the mean of the differences different from 0? Okay. So you want to stay on top of your words. But after that, right, we're testing to see, oh yeah, checking the assumptions. I'm going to skip ahead. Give you the answer so we don't have to read all those. Since the students are randomly sampled, right, that touches on our independence. So randomly sampled, that's something to look for when we're checking our assumptions. That's always one of the assumptions. So if you're completely blanking on your assumptions, just write random check and maybe make sure that it says somewhere in the blurb they were randomly sampled, and then you can write random check. Good enough. It's part marks. 200 students is less than 10% of all high school students. I'm not too concerned about the 10% condition, but our sample size should be less than 10% of the population. Otherwise, we're introducing dependence in our observations. And we can assume that the students are independent of each other, right? The two samples are not independent, but the students are independent of each other. So here, students are independent of each other. Oh. Yeah. Okay. Oh, you know what? I should have kept, I'm regretting my slide decision right now. Let's do this where I grab this. And let's just do it together. The answer is on the next slide, but that's okay. The observed average difference, okay, that's your X bar of the differences between the two scores is negative 0.545 points, right? So I give you what it is, and then you have to plug it into the equation. So let's make a note here that X bar of the differences is negative 0.545. The standard deviation of the difference is 8.887. So that means that the standard deviation of the differences is 8.887. Do these data provide convincing evidence? And as soon as you see evidence, you know you have to do a full hypothesis test. All right, all the steps, everything. And so of a difference between the average scores on the two exams, and then we're told to use an alpha level of 0.05, which is our default anyways. Right? So I'll start with our assumptions so you can see how brief we can be. Independence. Students were randomly sampled. Normality. Our sample size is 200, right? N is 200, which is greater than 30. So we can assume normality. We also saw the histogram. The histogram looks approximately normal. And so, but usually I don't bother giving you the histogram on the test, for example. And so then this, you would just say this. What if your sample size is 20? What would you have to say then? You'd have to say our sample size is less than 30. So we assume the distribution is approximately normal, right? If you can't justify it by being larger than 30, then you have to say, well, here's one of the assumptions that I'm making, right? I'm going to keep going, but I am assuming that it follows a normal distribution, right? Or looks approximately normal. So, good. Now we're ready for our hypothesis test. At the door. Step 1. State the hypotheses. All right. Key thing, if you've determined, so you read those questions, and I put a note at the top of those, the practice for test 2. The first thing I want you to do, or try to do, is just read all those questions. Don't even try to solve them or anything. Just read them and try to figure out what type of question it is, right? And then force yourself to look at the formula sheet and say, that's where I'm stuck, right? For this question, this is all I have, nothing else matters, right? For this question, this is all I have, right? So figuring out what type of question you have is going to be very important. We have at some point determined, or at many points determined, that this is a paired data type of question, right? And so from our formula sheet, oops, you're reminded that, okay, then my null hypothesis is that mu diff is equal to 0. And as soon as you figure out that you have paired data, you think, score, I don't have to think about my null hypothesis so much. Mu diff is 0. Our alternative hypothesis, just like always, has to be about mu diff and how it relates to 0, right? So I'll just write out those components, and then I just have to read the question to make sure that I have the right sign for my alternative hypothesis. So let's go back and see here. Do these data provide convincing evidence of a difference between the average scores on the two exams? And so here, this means that my alternative hypothesis has to be not equal to, right? I don't care if one's lower or one's higher or some version of that. I just want to know if there's a difference, if the mean difference is different from 0. Don't worry, it gets worse. Later, we're going to talk about the difference in the means being different from 0. Oy. I always make a note that this is a two-sided test, right? If I'm concerned about only less than or only greater than, then I have a one-sided test and I check whatever tail I'm interested in, right? But this makes it a two-sided test, or two-tailed if you want. I need that in step 3, but so it's going to feel like a long time ago that we set up our alternative hypothesis by the time we get there. So that's why I just make a note to myself to remind me later. Oops. Step 2 is whatever calculation. So if I give you the hypothesis test and I give you the null hypothesis, and then I've accidentally given you a default alternative, sorry about that. Sorry, not sorry, I guess. Whatever calculation follows your null hypothesis on your formula sheet is the test statistic, right? So step 2 is do the test, which sounds cooler than calculate the test statistic. Or maybe it doesn't, I don't know. You're going to calculate the test statistic. And the test statistic in this case is T is equal to X bar of the differences minus 0, right? We want to know how far is our sample mean difference from 0. And so this is always 0. You don't even have to write it out if you don't want to. Divided by the standard deviation of the differences divided by the square root of the number of the differences. Page here. We have all these components from the question. So now it's a matter of just plug and chug. Negative 0.545. You can write minus 0, I'm not going to. Divided by 8.887. Divided by the square root of 200. I guess I don't have it. I don't have it pre-baked. Uh-oh. Get my Martha Stewart on. 8.887 divided by the square root of 200. I like to find the standard error first, and then negative 0.054. Nope. 0.545 divided by the previous answer. I get a t of negative 0.8672739.862. Hopefully, okay, looks like that jives. But it's been a weird day, so maybe not. Can I just take a peek at the solutions? Just to make sure. Oh, phew. Just that kind of day. How many decimal places? Let the table be your guide. You've calculated a t, so you need to use the t table, and you'll see that the t table gives all its t's to 3 decimal places, so you're going to round properly to 3 decimal places. And so here, 3 decimal places, so I get t is roughly negative 0.867. What does a t of negative 0.867 tell us? It tells us that, well, the short of it is the mean or sample mean difference of negative 0.545 is not very far from 0, right? In fact, it's 0.867 standard errors below 0. That's not very far at all, right? So already we're gearing up to not having enough evidence to reject H naught, right? Just from this T, we have to have the p-value to back it up, right? But already we've got a good idea of where our conclusion is heading. Okay? So now step 3, find the p-value. Now that you have this T, this is everything else is gonna look exactly the same as Monday, right? It's just how you got there was arguably the same, but just slightly different. What do we need to do? We have to find the p-value. So to use the t table, we have to have the, degrees of freedom. Using degrees of freedom equal to n diff minus 1. It seems annoying to write out n diff or the subscript diff, or you can use d's, that's totally fine. But I want you to indicate to me, because I'm marking your work, right, that you know that it is the difference, right? So just show off everything that you know, and that'll be great. 200 minus 1, which is 199. I'm going to go to my t table, but spoiler alert, there is no line for 199. What's the rule? We have to bump it down to 100, right? Or down to whatever the closest degrees of freedom is. Okay, so I'm trying to find, I'll delete this because that's just a fake news. So here's my degrees of freedom. 80, 100, 1000. I have to use 100. Right, because we always have to round down. Our other option would be 1000, but that's saying that you have a sample of size 1001 when you actually only have 200, right? And so that's claiming to have more reliable results than you actually do. So that's bad. So that's how I remember to bump it down, right? You're safer to say, oh, I only had 100. Psych, I had more. So here I'm going to say, but using degrees of freedom equal to 100 in the table. Now, if you're using Excel or any sort of software, you would use 199. That's great, right? Unless you want your value to match the table, then you should use 100 because that's what you're using in the table, right? Okay, so first thing you have to do is tell me what your degrees of freedom are. Then you're going to outline the steps that you took in the table. So now I like to do a little preamble. We find that, and I like to put my T in the middle of the page because then I'm going to have values on either side of it. And we have to take the absolute value of T. So the absolute value are those vertical bars. T equal to negative 0.867. Whoops. Right? Take your calculated T, wrap it up in absolute values. And then because I don't want to deal with inequalities, I always use the same setup. Some value is going to be less than this value, and some value in the table is going to be larger than this value. So I'm going to take a picture, it'll last longer. Oops. So here, when I take the absolute value of negative 0.867, that makes it positive, right? 0.867. So then I try to place my 0.867 and it lands somewhere in here. The benefit of writing these values down, right, is that if you did something silly and you told me that it was between these two values or something like that, as long as you followed through, then I can be okay with that, right? You just made a silly mistake, you looked and you jumped over or something like that. And so here, what I'm gonna do is I'm gonna write out 0.845 and 1.042, right? Just to show that T is somewhere between these two values. Yeah. Bump this down because it's not part of our answer. We're using it to find our answer. So now we're on to the p-value, right? And this is where I like to show off whether you have a one-sided or a two-sided p-value. And I want you to show off as well. We determined earlier, I told you it feel like a long time ago, right? We have a two-sided test, so we need a two-sided p-value. So the two-sided p-value is going to be between two values, right? So going down here, I'm deciding I want a two-sided p. So then my p-value is going to be somewhere between 0.3 and 0.4. Remembering to read or write them from right to left because they're decreasing as you move out further into the tail, right? Your T is increasing as you move across the page, but that means that the area in the tail is decreasing, right? So our two-sided p-value is somewhere between 0.30 and 0.40. That matches our gut reaction when we found our T was relatively small, right? Not very far from 0. And so this is a large p-value, right? So again, we're not going to have enough evidence to reject H0. Time for the conclusion. Right now you've got a range for your p-value. You can easily, and I make you do it in the assignments. I make you use any sort of software that you want. I show you how to do it in the lab this week, how to find probabilities for T's. And so you could use Excel if you want, but any online calculator will do. Okay. Just make sure that you match whatever degrees of freedom you had in your table, right? Not the real ones. Usually it's not the real ones. And then I get you to put the actual p-value in there. And what you'll see is that it's somewhere between 0.3 and 0.4, right? So close enough. So now we're ready for our conclusion. So step 4 is our conclusion. 3 parts to our conclusion, same 3 parts as always, right? First, you compare your p-value to your alpha level. Is it less than your alpha level? Is it greater than your alpha level? Or rather, is it not less than your alpha level? All right. So since our two-sided p-value, I have to think about it. Oops, p-value is between, so notice it feels weird initially when we have a range for our p-value, but we can still draw our conclusion, right? This entire range is above 0.05. In fact, it'll never cross 0.05. Yeah. So it's either going to be on below 0.05 or above 0.05. But since our two-sided p-value is between 0.30 and 0.40, it is not less than the alpha level of 0.05, right? Tempting to just say not less than the alpha level, but you want to explicitly say what it is that you're comparing it to. Which means we do not. So notice how I use the not and the not, right? We do have enough evidence to reject H naught, or if it's not less than, then we do not have enough evidence to reject H naught. We do not have enough evidence to reject H naught. What was the question? I'll steal it from here conveniently. Do these data provide convincing evidence of a difference between the average scores on the 2 exams? I would just take this, copy, paste. These data do not provide convincing evidence of a difference between the average scores on the 2 exams, period. Tedious, but you take your question, reword it as an answer. Oops. Oh boy, now I've made a mess. There. And then you're done. But your conclusion is going to be 3 marks, right? Because there's 3 parts. And I'll say now, everyone loves to forget this one because by the time you've done all of the other work, you're just spent and you feel like that has to be it. But you didn't actually answer the question. It's an easy mark because you just reword the question as an answer, but it's often forgotten. Ta-da!
Where are they getting that 0.1927 from?
They're using software, I think.
Okay.
Yeah.
So that the 0.1927 is the actual t-value?
Is the one-sided p-value. So I think this is coming from software. And they're probably using 199 degrees of freedom, I'm guessing. I must have cut an important slide where they showed where that came from. But then they had to multiply it by 2. But notice that 0.3854 is between 0.3 and 0.4, right? 0.3854, so sold. Okay. Good. This one, I'm gonna skip because I actually didn't like where it led you. you know how to think about p-values to reject H naught and things like that. So we'll move on to the next one. What if we have to construct a 95% confidence interval for the average difference, so mu diff, between the reading and the writing scores? Would you expect this interval to include 0? Gonna go with yes. Why? Because a confidence interval, right? If I'm 95% confident that 0 is in the interval, right? So here, if I have 0 here, or maybe, sorry, I shouldn't have put it in the center, that's misleading. But maybe if I have 0 here, right? If 0 is in the interval, then that's equivalent to failing to reject H naught, right? And so this is the same as we do not have enough evidence to reject H naught. So we can use a confidence interval, and we've seen this before with proportions, and it works the same for means, right? And so we can use a confidence interval, but a confidence interval corresponds to a two-sided test. And unless I cut the slides, which I don't remember right now, we'll see an example of. But yes, we do, and we can calculate it. The only one that I want to focus on is finding that critical value for the confidence interval. In fact, I'm going to grab the formula here. Whoa, long time ago. Copy. I'll put it here. Put her there. I'll highlight the yes because that's what we said. And so we have X bar of the differences, we have S of the differences, and we have N of the differences. So I trust that you'll be able to do that calculation. But for practice, let's find that T star. So if we want to make a 95% confidence interval, we need to remember how many degrees of freedom we have. Let's say, well, we have degrees of freedom is N diff minus 1, which is 199, but using 100, or I should say DF equals 100. From our formula sheet, or sorry, from the table, man, just a weird day. Again, well, just removed it. If I want a 95% confidence interval for a T star, right, then I need to go and I stop at whatever degrees of freedom I have. And so here, 95, 1.984 is going to be my T star. T star is 1.984. That's going to be different from here, and that's why I wanted to show you. Here they use 1.97, but that's using software and 199 degrees of freedom. And so there's going to be a subtle difference, but nothing crazy. So this is from software, probably with degrees of freedom equal to 199. Otherwise, they'd be more similar. Okay. Ooh, risky business. Difference of two means? I already declared it's not on the test. Do I start it? Well, there was one thing that I wanted to just mention, because if you hate the Z table, and maybe you do, right? We used this table, this T table, to find what the Z star would be for a confidence interval for proportions, right? What did we do? We said, okay, if I want a 90% confidence interval, for example, then my Z star would be 1.645. And then for T's, what we said was, well, you do the same thing, but you just stop at whatever degrees of freedom you have. Okay? And the reason for that is because your T distribution, as you collect more and more of the population, becomes the Z distribution. So Z star, or Z, is really just the T distribution at infinite degrees of freedom, okay, technically. So what could you do? If you don't like the Z table, which is fine, you could just use this line here, right, for a Z. And you could say, okay, I found a Z, and let me just, maybe I'll grab a copy of this, but without this line. And I mention it because I have taught it this way before. Well, one year I was so sick of all the tables that I only used the 68, 95, 99.7 rule and then software for everything else. Crazy, right? What? How could you do that? Well, it's just a sloppier version of this, right? With only 3 points, 68, 95, 99.7. Use software for the rest. All right, you could do that. We're not going to, I don't want you to, but I did do that at one point. So what we could do, we could use the T table for probabilities associated with Z. Using the Z star line as our degrees of freedom. So for example, if you calculate that your Z is 2.734, I don't know. I'll put a little calculated here. Just to emphasize that I made it up, but also something that you've calculated. What could you do? You could take your 2.734, or let's show off, let's make it negative. Right? Then using the T table, the absolute value of Z equal to negative 2.734 is going to be between, moving out, 2.734, somewhere between 2.576 and 2.807. Right? So same structure as the T's, 2.576, 2.807. Now you have the one-sided P. You get a range for the p-values, whereas the Z table gives you a more precise p-value. It's still not as precise as it could be with software, right? But now you get a range for the p-values, and we could confirm it with the Z tables. So let's say our one-sided p-value, because I'm lazy, would be between reading from right to left, 0.0025 and 0.005. We can confirm that, right, by finding the more precise p-value in the Z table. We can confirm with, oops, I always combine with the into one word, with the Z table, right? So now I had a Z of negative 2.734. Whoa, that's a nasty normal. I mean, I can't look at that. Whee, nice. A one-sided p-value is going to be the area in the tail. It's always the area in the tail, but if it's negative, it's in the lower tail. And if my Z is positive, it's the area in the upper tail. And if it's two-sided, I have to find the area in whatever tail I'm in and multiply it by 2. So now I can use the Z table. I'll use 2 points. Negative 2.73 to 3 decimal places. Because Z table has 2 decimal places instead of 3, that's okay. So now if I go to my negative Z side, negative 2.73. I'll copy. The area to the left is 0.0032. And so using the probability that Z is less than negative 2.73 is 0.0032. 0.0032 is between 0.0025 and 0.005. Right? And that's how it works. So it's confirmed. So if you want to forget all about the Z table and only use the T table, because now I warned you, you're gonna like the T table more the more you use it. It's more compact, you can figure out what's going on in there. It's easier to handle, I think. So now if you prefer to use the T table on the test on Monday, you're more than welcome to, right? Just make sure that you write out exactly the same steps that we did for our T's and follow that same structure, and that's allowed. Okay. I'm not going to start 2 independent sample means, but it's really fun. You've got the formula sheet, you can do it, but we'll save it for after the test. Any questions? Well, if you do, let me know. Otherwise, I'll see you on Monday for our test. I release you to make up for all the times I go over.